Hello, this is Dr. Miller, and I'm going to go over how to answer the questions on Pre-Lab 2.1. So this is due the week after the 16th, so that would be the 23rd. It's due the week of the 23rd. So I think the first 1 and 2 questions are something you can figure out. It's going over how to figure out how many students are in-state students. You're given how many students are out of state, how many students are international students. So you would take 100% and subtract the 22% and the 18% international students to find how many students percentage-wise are in the freshman class from out of state. And then you want to write a sentence on the part B on how this demographic information example of percent composition. So now we're going to look at compounds and look at the individual elements and relate that to percent composition. So let's go down to question number 2, and there's a table here. So it asks us to calculate the theoretical percent compositions for each entry in table 2.1, and we are to include a sample calculation in the space provided. So let's do the first one as an example, and then I will show you a little basis for the last one, and then you can figure the rest of them out on your own. So our first compound is magnesium oxide, MgO, and the element of interest is magnesium. So we want to figure out the atomic mass of the element of interest, and then we want to figure out the molar mass of the compound, and then we're going to find the theoretical percent composition of the element of interest. So we have to go to the periodic table. Now the periodic table will show us the information that we need to use to calculate. So we're interested in magnesium and in oxygen. So we look at magnesium, and the atomic number is 12, but what we're interested in is the atomic mass. And that could be in atomic mass units. So that could be AMUs, but the same number also applies to grams per mole. And that's what we're interested in, because that's what the table has it set up with, is grams per mole. So 24.31 grams is how much a mole of magnesium weighs. So a mole is something that we can use on the reaction level. A mole of magnesium oxide reacts with a mole of oxygen. A mole of magnesium reacts with a mole of oxygen to form a mole of magnesium oxide. So it's like having a dozen eggs. You know that a dozen eggs contains 12 eggs. A mole of anything contains 6.02 times 10 to the 23rd items. So there are 6.02 or 6.022 times 10 to the 23rd atoms in 1 mole of magnesium. It could be a mole of oxygen, but that's Avogadro's number. But we're going to just use the concept that that's how many atoms, but we're going to have a whole gram of them. We're going to look at a whole mole of them and how many grams that weighs. So the atomic mass of the element of interest in grams per mole is 24.31. We get that from the periodic table. So we're going to put 24.31, and that's grams per mole. And then it wants to know what the molar mass of the compound is. So we have 1 magnesium. Let me move this a little bit. We have 1 magnesium and 1 oxygen. 1 mole of magnesium, 1 mole of oxygen. So we have 24.31 grams of magnesium, and then we need to go back to the periodic table and look at oxygen, and oxygen is 16.00. Now you'll use oxygen so much this semester, it doesn't hurt to go ahead and memorize that, but you'll always have the periodic table with you on any quiz or exam you have. So you wouldn't have to memorize it, but it's a nice even number, so 16.00. So 16.00 grams per mole. And we can also indicate that there's 1 of each of these. So 1 times that, 1 times that. So then we would add them together. So we would get a total of 24.31 plus 16.00. We can use a calculator, or I can just do it by adding them. 40.31. And that is our grams per mole of the entire compound. The molar mass of the compound is 40.31 grams per mole. So we got that by adding up the individual atoms, or the individual elements. So now we want to find the theoretical percent composition of the element of interest. So of that 40.31 grams, only 24.31 grams are represented by the magnesium. So in order to find the theoretical percent, we take the item of interest, or the element of interest, and divide it by the total mass of the compound times 100% to get our theoretical percent. So we're going to take 24.31 divided by 40.31 times 100% to get our answer. So that will be our answer in percent. So you'll need to do that. Oh, that should be 31. Okay, so 24.31, which is our magnesium, and divided by the total, which is 40.31, times 100% will give us our percent. So now let's go look at the last one to just make sure that you're confident in how to calculate that, because it has a lot more parts to it. So copper and carbonate and hydroxide is what we're interested in, and the copper is the item of interest. So now we have to find the atomic mass of the element of interest. So we look at copper, and copper is a transition metal, and it's right here. So it's 63.55 grams per mole. 63.55 grams per mole. Now this is where we have to really understand how to interpret our symbols over here with our compound, and that's to find the molar mass of the compound. So molar mass of compound in grams per mole. So copper is 63.55, but we have 3 of them, so we have to multiply 3 times 63.55 in order to find out how much of the compound represents the copper. So then we need to look at the carbon. The carbon's next. So how many carbon atoms are there, or moles of carbon, either one? So we have them in the parentheses, so there's no subscript right behind the carbon, so we need to look at the subscript that's behind the parentheses. So there are 2 carbons in this compound. So 2 times, and then let's go to the periodic table. The molar mass of carbon is 12.01, so 12.01. Now we need to look at oxygen. Well, there are 3 within the parentheses, but there's 2 altogether. So 2 times 3 is 6. But when we go on look, there's another oxygen here in the hydroxide, so there's 2 of them because there's 2 hydroxides. So we have 3 oxygens in the carbonate, and we have 2 carbonates. And we have 1 oxygen in the hydroxide, so we have 2 oxygens. So we have 6 oxygens plus 2 oxygens, so we have a total of 8 oxygens. So 8 times and 16.00. Now we have left is our hydrogen. So our hydrogen, how many do we have? We have 2 of those. So now we need to look at hydrogen, and that is 1.008. 1.008. So now you need to multiply 3 times 63.55 and get a number, 2 times 12.01, get a number, 8 times 16.00, get a number, and we can put equal signs there, and then hydrogen 2 times 1.008 and get a number. Then you're adding all of those up to get the total molar mass of the compound. Then to find the theoretical percent composition of the element of interest, we have to consider that we have 3 times 63.55. So whatever that number is what the is represented by the copper. So the amount of copper, and we could just go ahead and figure that for demonstrations purposes. So 3 times 63.55 is 15, 16, 0, and 190. 190.65, let me just double check that. 63.55 times 3, 5, 6, 10. Yes, 190.65 is our grams per mole. Then we're going to divide that by our total and take that times 100% to get the percent composition. So you'll do that for each of these, and remember that there's 3 magnesiums and 2 nitrogens in this one, 1 copper, 1 oxygen, 2 coppers, 1 carbon, 3 oxygens plus 2 oxygens, so 5 oxygens and 2 hydrogens for that. So be able to remember how many you have, multiply, and then you're going to divide the total mass of the element of interest by the total molar mass of the compound. And that's how you'll complete pre-lab for activity 2.1.